So first let's draw the shape, and then we can decide, do we want to use a horizontal or a vertical rectangle to get to do the rest of the steps. All right, so this has a height of 3 and a width of 3. And then this top curve is defined by y equals 1/9 x cubed. So again, if we decide to use a horizontal rectangle, its height is going to be dy, and then everything will be in terms of y. If we choose a vertical rectangle, its width will be dx, and everything will be in terms of x. So kind of the first rule of thumb is look at the functions involved to help guide if you would rather use a vertical or horizontally oriented rectangle. So if we look at the function, what we want to do is look at, if we isolate the y term, what the other side looks like. If we were to isolate the x term, what the other side would look like. In this case, y is already isolated. So y is 1/9 x cubed. So we have a whole number power here. But if we think of the alternative, we would have x equals cube root of 9y. Again, cube roots we want to usually avoid if possible. So this tells me that we're probably better off using x as our variable that we're going to integrate with respect to. So that means we want to use dx as our differential piece, which means that we would prefer to use a vertically oriented rectangle. Again, that's because if it's vertically oriented, the width of each rectangle is dx. If we have a dx, everything will be in terms of x, and we'll see when we get to the integration step how it's easier by hand to use x rather than using y. Again, both methods, either method, vertical or horizontal, will arrive at the same answer. So where we want to start, we want to draw this kind of generic rectangle here. But what we're going to find, the definitions we're going to find are good for any rectangle because, again, the premise of what we're doing is we're making all these little rectangles out of this continuous piece, finding their area, and adding it all together, and then that's going to tell us the area of the entire shape. So what we want to start with is finding this, what I call dA. That's the area of any one of these rectangles. So the area of a rectangle is going to be its length times its width. So each one has a width of dx. So the equation we write here has to be true for any of the rectangles that we have. So if we see how these rectangles are oriented, every one has its base at 0. However, the height of each rectangle is different. So what can we put in here for the height of every rectangle to put into this function? Right, so the top of every rectangle is located on this curve here, and this curve is defined as y equals 1/9 x cubed. So because we're using dx, we need x in this equation, so we need y equals 1/9 x cubed, so its height is 1/9 x cubed, its width is dx. So this now describes for any rectangle we draw what its area is going to be. All right, questions on this step? So now what we want to find is where is the centroid of any of these rectangles located. So that's going to be, again, defined from the x-axis and the y-axis. So we need to find, this is y tilde, and then that is going to be x tilde. So when we use the single integration method, one of these is always easy. It's going to be, so in this case, x tilde is just going to be x. So when we choose dx, x tilde is x. When we choose y, y tilde is going to be y. It's not as simple, though, to find y tilde. So how do we find where's the location for any of the rectangles? How far is its centroid above the x-axis for any rectangle? Right, because they're rectangles, we know for a rectangle that its center is going to be at half of its height and half of its width, which in this case is located at x. But half of the height, we know the height of each rectangle is 1/9 x cubed. So half of that height, this measure, is always going to be then 1/18 x cubed. It gets a little bit more complicated, as we'll see in the next example, because we're always measuring from the x-axis to get to the y tilde value. In this case, all of the rectangles have the same base at y equals 0, and then their height is different. It's y equals 1/9 x cubed. So we have dA defined, x tilde defined, y tilde defined. Now we can go and do the calculus steps. Any questions to this point of what we're looking at? Yeah. Because for this, it's half of the height of the rectangle. So everyone has a height of 1/9 x cubed, so half of that is 1/18 x cubed. Any other questions? I'll find these.
That goes for every rectangle.
Right, so for all of these are all the same way. So even though this one's shorter, what does that, well, that means that the y value is smaller, so its y tilde value is also smaller. So because they're all defined the same way, these are good for every rectangle between x is 0 and x is 3. You could have more complicated shapes where these definitions are not true for all of the rectangles, and then you would have to kind of integrate it in different sections. But for this one, since it's continuously defined from x equals 0 to x equals 3, these are all good. So we'll start by finding the area of the shape. So from the previous slide, the area is going to be the integral of dA. From a lower limit to an upper limit. So we'll go A to B just very generically. So dA, as we've defined it, using vertical rectangles, is 1/9 x cubed times dx. Because everything's in terms of x here, the bounds are also in terms of x. So what this says is we want to go from our first rectangle to the last rectangle. So the first rectangle is located all the way over here when x is equal to 0. And we're going to add all of the rectangles until we get to the last rectangle here when x is equal to 3. So our bounds of integration in this one are x equals 0 to x equals 3. Potentially, you have to be careful of, are your bounds defined by x or defined by y? Because the bounds will change depending on if we use a vertical or a horizontal rectangle. Right, so we can take the antiderivative of this, so we'll get 1/9 times 1/4 times x to the 4th, evaluated from 0 to 3. And if we carry through that calculation, we get that the area of this shape is 2.25 feet squared, or square feet. And for this class, all the integration we're going to be doing will be polynomial, so you won't have to worry about transcendental functions or things like that. So by hand, these should not be too bad to be integrating. Questions on finding the area of the shape. Right, so again, that's the area, if we look at the picture, the area of the blue shaded section, 2.25 square feet. So now we want to find the location in the x direction of the centroid. So that's defined as x tilde dA, or the integral of x tilde dA, over a, again from that previous slide. A we just found in the previous part to be 2.25, so the denominator we're done. So now we have to work on the numerator. So it's x tilde times dA. We have a definition for dA. We have a definition for x tilde. So it's x tilde times dA. I can pull out that 1/9 again. I now have x to the 4th dx, since I have x times x cubed from x tilde times dA. I can now find the antiderivative of this, so it's going to be 1/9 times 1/5 times x to the 5th, evaluated, oops, the bounds here are still 0 to 3. Evaluating this at 3, evaluating at 0, we get that the numerator is 5.4 over the 2.25. So the x bar value is 2.4 feet. So on the picture, to get to the centroid, we start at the origin, and then we travel 2.4 feet to the right. And then we need one more coordinate to find exactly where would we, if we wanted to balance this on our finger, where would we have to place it so that we could do that? So that last piece we need is the y bar value. Any questions on the x bar value? So y bar is defined as the integral of y tilde dA over a. So again, same denominator as before. Same bounds of integration as before, but now we have to take y tilde and multiply that by dA. So I can pull out the 1/9, pull out the 1/18. I have an x cubed times an x cubed gives me x to the 6th times dx. Taking the antiderivative of x to the 6th, I get 1/7 x to the 7th. Evaluate that at those different bounds, 0 and 3. Is going to give me 1.93 over 2.25, which simplifies down to 0.857 feet is my y bar value.